Good morning. We're going to be taking a look at some similarity in right triangles, and in particular, we're going to start looking at something referred to as the geometric mean. And the geometric mean will show up in competitive math from time to time in particular math counts. Well, let's start with the warm-up. Well, we have the square root of 72, so we're looking at what goes into 72. That is a perfect square. Well, 9.
As for the first time in forever.
Thank you.
She's pretty good.
Excellent. Thank you. I hope you enjoyed that little musical interlude. Square root of 9 times square root of 8. Square root of 9 is 3. 8 can be broken down into square root of 4 times square root of 2. That's 2. So this is equal to 6 times the square root of 2, because 3 times 2 is 6. Similarly, we have the square root of 9 times the square root of 3. That's 3, so this is equal to 3 root 3. Using cross multiplication, we know that 3 times 8, that's 24, is equal to 5x, divided by 5, divided by 5, and we get get x is equal to 4.8, or 4 4/5. Now this one's a little bit trickier. We're going to divide it by 2, divided by 2, so we get x squared is equal to 25. The opposite of squaring is square root, and so we get x is equal to, now the tricky part is we got x could be -5 and +5, so we have to remember that there are two possible answers. All right, since that is out of the way, let's take a look at Theorem 8-1-1. And this is a theorem that has to do with right triangles. So I'm going to draw a right triangle. And then I'm going to draw an altitude, which obviously is going to meet at a right angle. I'm going to call this A, B, C, and let's put D here. Now, if I'm looking at this drawing, I see 3 separate triangles. I have triangle A, B, C. It's obviously the biggest one. Now, the interesting thing with right triangles and the altitude of a right triangle is that we will end up making 3 similar triangles. So triangle ABC is similar to triangle ABD, which is similar to triangle, oh, and I hope I got the order right. No, I did not. Oh, wait a second. So from the right, no, I definitely did not get the order right. So A corresponds with D. And then we have, so we went from A, we went along the hypotenuse. So from D, oh no, we didn't go along, we went along the shortest side. We went to B, and we went to A, which is similar to triangle. Well, starting at the right angle is again D, shortest side A, C. So all 3 of these triangles are similar, which brings us to some properties of the line segments AD, AB, AC, BC, and BD. And we're going to talk about those in the geometric mean. So looking at the corollaries, 8.1-2 and 8.1-3, the first thing I'm going to do is I want to make a little diagram that will serve for both situations. So I'm going to make the same drawing. Of course, well, whatever. I'm going to call this side A. I'm going to call this side B. Anya, can you turn off the heater?
Yeah, why?
As soon as the projector starts putting on the cooling fan, it's time to take the heater off. We're going to call this entire side C. I'm going to drop that altitude again. And I'm going to call the segments of C, x and y. And so corollary 8-1-2 says that the length of the altitude to the hypotenuse of a right triangle is the geometric mean of the lengths of the two segments of the hypotenuse. Well, what does that mean? Well, what is a geometric mean? Or how do I find a geometric mean? Well, what that means is we have the height here. We know that the height squared is going to be equal to the lengths of the two segments of the base or of the hypotenuse multiplied together. So similarly, we can say h is equal to the square root of xy. For 8-1-3, we have a similar geometric mean, where the lengths of the legs of a right triangle is the geometric mean of the lengths of the hypotenuse and the segment of the hypotenuse adjacent to the leg. That's a lot of words. I think an equation or a diagram would make more sense. So what it's saying is a squared is going to be equal to c times x times c. So this side length here is going to be equal to, or the short side is going to be equal to this side right here that it's adjacent to times the overall length here. Now obviously I can also say that a is equal to the square root of xc. xc, that sounds like a great sport. Maybe we should learn some more about that. And then obviously if this works where a squared is equal to x times c, we could turn that around and say b squared is equal to y times c. Or b is equal to the square root of yc. Okay, well, how does this happen? Or how does this affect a geometric sequence? Well, we are trying to find the fourth number of this geometric sequence, which means I need to find the geometric mean to find this value, and then I can take the geometric mean of this value and this value to get the fourth value. To find the geometric mean, we're going to multiply 10 and 4 because they're equidistant from here. Sorry, 10 times 40, which is 400. And then we're going to take the square root, which is 20. So the geometric mean of 10 and 40 is 20. Well, how do I find the geometric mean between 20 and 40? Well, we multiply 20 times 40, and that's going to be 800. And so we're going to take the square root of 800, and we're going to get 20 times the square root of 2. So what is a geometric mean anyways? That is really a wonderful question. So the geometric mean, sorry for that awkward pause, the geometric mean of two positive numbers is the positive square root of their product. In other words, if we have this proportion, a over x is equal to x over b, well, using cross multiplication, just like we did here, we will end up with x squared is equal to ab. So the geometric mean of a and b is the positive number x such that, obviously I'm reading, x is equal to the square root of ab, or x squared is equal to ab. And so that's what we're going to be working on today to solve problems.